a wave-powered electric generator. My name is Graham Piper, and I was part of the financial and communications teams. We are located in northeastern Pennsylvania, which is approximately 265 miles away from MIT. We are located on the shore of Lake Wallenpaupack. It's a hydroelectric generating lake that was built in 1926 by PPL Corporation by damming the Wallenpaupack Creek. And for those of you who are wondering, Wallenpaupack is derived from the Lenni Lenape Native American word for stream of swift and slow water. This describes this stream as a series of slow-moving pools with interest-risk cascading waterfalls before it was dammed. We are located in the heart of the Pocono Mountain region, which is a popular vacation destination. On the right is a picture of our beautiful Lake Wallenpaupack that is 13 miles long and has approximately 52 miles of shoreline. The Wallenpaupack Area High School itself is a public high school with approximately 1,200 students in grades 9 through 12. Our team is comprised of 14 students from the Wallenpaupack's Gifted Education Program. This program provides enrichment opportunities in fields tailored to students' individual interests. Inventiveness has always played an important part in our program by expanding our learning outside of our regular classrooms.
Hi, I'm Christian Sonsby, and I was a member of the technical team. So, students in our Gifted Education Program have participated in the National Engineering Design Challenge and the Ability One Design Challenge for many years. These challenges urge students to design and develop an assistive device to aid people with disabilities in the workplace. Achieving national final spots in both these competitions has led to us applying for a Lemelson MIT grant. So, in the spring of 2013, we started brainstorming ideas for an invention. We were initially inspired by the technology of a shaped flashlight, which is a flashlight that is powered by a magnet passing through a copper coil when shaken, as Adam just demonstrated. Our ideas evolved from there when one day we noticed that the motion of Doc moving with the waves offers the same linear motion needed to pass the magnet through the coil. And that's how we got the idea for our lake wave generator. We determined that our device could potentially solve a major safety issue that we have on the lake, which is lighting. The lights are mounted on the shore at night, but since AC electricity is not permitted to be used out on the docks, they are very poorly lit at night. Our initial design was basically an enlarged version of the shaped flashlight. We wound copper coils around plastic tubes and slid disc magnets through the coils. We thought that fastening the copper coils to the dock and holding the magnet stationary in the water would generate electricity as the dock moved with the waves. This drawing is part of our original grant application. As you can see, the dock will move up and down with the waves, which will pass the copper coil over the magnet, which is anchored to the lake bed. Unfortunately, when we hooked this device up to an oscilloscope, we realized it did not nearly generate enough electricity to power the LED as we expected. At this point, we're at a major transition period, and we're really struggling. Fortunately, we were contacted by Mr. Paul Fusil, who's an engineer at Woods Hole Oceanographic Institution, who specializes in working with electronics and water. His advice started to have a profound impact on the progress of our team. Once we determined that linear motion would not sufficiently power the LED bulb, we started to research rotary motion. The hydroelectric generators for our lake use rotary motion, as almost all electricity generators do. A copper coil rotor spins inside a magnetic stator, producing electricity. So we looked into it and determined that we could use modified... Oh yeah, I had one job. Okay. We looked into it and then found that we could use modified servo motors to act as generators. Since motors require electricity to turn, the opposite is also true. Turning a motor manually will generate electricity. So we mounted the servo motors to a metal arm which moves vertically as the dock rises and falls with the water. And that vertical motion will turn gears inside the servo motor, which will convert the kinetic energy into electrical energy.
Hi, I'm Sebastian Aparicio, and I was a member of the technical team. So to test the harsh winter, we decided we should build a wave tank. Our wave tank consists of a 50-gallon aquarium, lava-produced waves, and floating dock. Attached to the dock is a modified servo motor attached to a stationary arm that sends electricity to a simple rectifier circuit to light an LED. see our wave tank at the showcase later today. The electricity produced by our reciprocating servos is essentially low power alternating current. We needed a circuit that would double the voltage so we had enough electricity to light the LED overnight and convert it to DC. So I worked with Mr. Fusil to design a schematic of such a circuit. It also included a pickaxe microcontroller that we can program to control the lights turning on and off with changing external lighting, like when it comes night and when it comes day. So, we ordered printed circuit boards based on the design in order to assemble the boards ourselves.
So we currently have 3 prototypes: the testing device that you see here, the cutaway model, and a fully refined model that we attached to a bouncing dock that you can see at our showcase. During our most recent test, we found that our device generates 6.5 volts and 13.5 milliamps of electricity to charge a 4.8 volt battery pack at 700 milliamp hours. And we programmed the Pickaxe microcontroller to turn on the device at 9 p.m. just about, and turn it off at 4 a.m. And at that time, the device is discharged to about 2.9 volts. So our lake level changes rapidly depending on rainfall and the amount of water used during hydroelectricity generation. This led to some issues when we were trying to find a way to anchor the pivot arm in a stationary position. As the lake level changes, so does the elevation of the dock. This motion made us realize that we cannot anchor the device to the lake bed. So instead we decided to use a suspended anchoring system that consists of 2 octagonal dampening plates that are connected by PVC pipe. The plates themselves resist motion in the water, which anchors the pivot arm while the dock moves, and it allows the servos to move up and down. So Christian's going to show you basically how this works. The dampening plates are connected to this arm right here, and yeah, the battery's disconnected right now, so you know I'm not cheating. So when he does this, here, a couple little parts. There you go. And this is why we have battery. So yeah, and then you have the battery connected, and this is the light sensor, which actually is an LED that you can use to do that.
Hi, I'm Rhiannon Bogart-Mandan, and I'm a member of the technical team. The technical team worked on tasks that revolved around building and designing various prototypes. We coiled wire and designed a small circuit board for our original generator, and redesigned various iterations to our current prototype. We also built and refined the anchoring system. For those of us who are more technologically adept, we went to work creating and soldering together the final design for our circuit board, and programming our microcontroller. The rest of us built the device's housing and the dock's mounting bracket. Many of us learned how to use hand tools, power tools, and soldering irons that we never used before. The financial team was in charge of managing our budget and organizing every single receipt that came in. Since our grant of $9,600 was outlined for our original idea, our spending did not match up exactly with our previously planned budget. However, we were able to sufficiently spend all of our money without any major conflicts. Some of the frequent vendors that we used were McMastercard, DigiKey Corporation, the Home Depot, and Amazon. We also received donations of 24 team t-shirts by Promo Gear and a $2,000 Empowering Educators grant from PPL.
Hello, I'm Gwen Jones for our communications team. On our communications team, we set up a Facebook, a Twitter, and a Blogger, which we use to post pictures and short updates to keep the public informed about our progress. We also created the brochures and business cards that we'll have available at our showcase. Also, instead of having an administrative team, our financial and communications team took on the role an administrative team would have. We have some advice for next year's teams. First of all, every team should be open to change. Our original idea, as you saw, changed drastically by January, and we had to completely redesign our original plan. This ties in closely with the need to be prepared for failure. Nothing ever goes perfectly as planned, and changes occur in every aspect of the design and grant process. It's also good to have multiple teachers involved. No one teacher can be everywhere at once, and so it's good to have different teachers there to facilitate each of the groups. Teams should make sure they find good mentors. Without the mentors we had and the help we received from them, we would not have been nearly as successful as we are today, especially for Mr. Polfusil. Lastly, teams should establish a flexible budget to account for all the unexpected changes that they will come across.
A little bit. There's still a few changes that we would like to make to our device. First, we would like to do some longer-term testing because our previous tests consisted of short weekends and lab tests. We would also like to research and refine the battery, power, and light connection so that we can increase the amount of energy efficiency from the device. We will also refine the anchoring system to reduce energy loss from excess movement. And lastly, we would like to measure the efficiency of the device by measuring energy conversion from wave action to light output.
We would not have been able to be here today without the help of a multitude of individuals that we would like to acknowledge now. Paul Fusil of Woods Hole Oceanographic Institution, and we would like to ask Mr. Fusil to stand for all of his help. We would like to thank Robert Condors of Ponderosa Valley Consulting, a renewable energy engineer. We would like to thank Meg Welker, Katie Lester, Jenna Wayne, and Mike Bennett, mentors from PPL. We would like to thank Promo Gear for donating our team t-shirts. We would like to thank WAS Industrial Arts teachers, Kevin McHugh, Ed Wargo, and Mark Watson, and engineering teacher Dave Heckman. PPL for the generous contribution of the Empowering Educators Grant, worth $2,000 to help us travel to Eureka Fest. Custom Circuit Boards for offering us a discount on our printed circuit boards. And Lighthouse Harbor Marina for letting us test our device on their docks. And finally, we would like to thank Mr. Schultz for all of his help. We would not have been nearly as successful as we are today without him. We would like to ask our other team members to stand to acknowledge them.
So I imagine when you were doing this, you thought about the competition for this. Can you talk a little bit about who you think those competitors